Siamo puntualissimi, dunque possiamo iniziare. Oggi è con particolare piacere che presento lo speaker del seminario matematico e fisico, che è il professor Enrico Valdinoci, un italiano all'estero, che ha studiato a Roma 3, ha fatto il postdoc all'Università di Austin in Texas, e successivamente il postdoc, il PhD, il postdoc poi alla scuola normale, è stato anche a Tor Vergata come professore associato, è stato all'Università Statale di Milano come professore ordinario, ora è full professor a Melbourne alla Western Australia University, è stato vincitore titolare di un ERC al Weierstrass Institute di Berlino, e ha un palmarès di premi notevole. Menziono l'importante Australian Laureate Fellowship del 2019, il premio Orazio Arena attribuito dall'Unione Matematica Italiana del 2023, e ieri ha conseguito il premio Luigi Vandamerio, che è attribuito dall'Istituto Lombardo Accademia di Scienze e Lettere qui a Milano. È un autore particolarmente citato, che ha fatto grande disseminazione, in particolare nell'anno 2002 quello del dottorato è il most quoted tra i giovani ricercatori che avevano conseguito il dottorato a quell'epoca, e negli anni 2016, 17 e 18 figura fra gli highly cited researcher del Clarivet Thomson Reuters. Ha una notevole attività, oltre che scientifica, editoriale, in particolare è nell'editorial board di Communication on Pure Applied Analysis, Discrete and Continuous Dynamical System, serie A, Topological Methods in Nonlinear Analysis, Advanced in Nonlinear Studies, e fornisce anche un prezioso contributo al board del nostro Milan Journal of Mathematics. Tra i suoi campi di ricerca, molto sommariamente ricordo il calcolo delle variazioni, l'equazione derivate parziali, in particolare le proprietà geometriche delle soluzioni, i problemi di frontiera libera, poi c'è il dominio dei sistemi hamiltoniani, teoria CAM, diffusione di Arnold, e scorrendo notevoli sono i risultati relativi alle applicazioni di superfici minime non locali. Chiudo ricordando brevemente, sintetizzando la motivazione dell'attribuzione del premio Amerio dell'Istituto Lombardo. In sintesi, i contributi scientifici di Enrico Valdinoci alla teoria delle equazioni derivate parziali e al calcolo delle variazioni, e ai problemi non locali e sistemi dinamici, distribuiti a partire dal 2000 in un'impressionante serie di oltre 250 lavori scientifici, sono di eccezionale rilievo e straordinario impatto. Oggi ci parlerà di non-local minimal surfaces, regularity, stickiness and sheeting phenomena. Chiudo con una domanda: are there non-Italian, non-speaking Italian in the audience? Since he can speak both in Italian and it's up to you. You prefer English? Gentilmente Enrico procederà, quindi cedo la parola e chiudo. Grazie.
Thanks a lot. It's a great pleasure for me to be here and to try to give this talk. So I will try to start from scratch, but please interrupt me if you feel I'm saying something confused or unclear or maybe wrong. So the idea would be to put together somehow two different topics. One is slightly more analytic, if you want, and the other more geometric, which is basically phase transitions and minimal surfaces. This is two classical topics in analysis, and also the link between the two is somehow one of the, I would say, great steps of recent mathematics. And if you want, the topic of phase transitions well dates back to van der Waals. It was probably formalized in the modern way by Landau. And the main idea is that the material could change phase basically because of two phenomena. One is that you have a potential, say, of this shape with a minimum that corresponds to a phase. And then when you, for instance, decrease the temperature, the material gets more organized and changes phase. So for instance, you lower the temperature and the potential becomes something like this. Then you lower the temperature again and a new phase arises here. You lower the temperature again, and this new phase is preferred to the previous one. I mean, this is probably describing, I don't know, the change of phase from water to ice. There is another kind of phenomenon that can arise in which the phase that is observed at high temperature actually becomes unstable and produces two different phases. And this is important for superfluidity or for material with lower resistance like superconductors. So you have a situation in which when you lower the temperature, you modify the potential from this configuration to a configuration like this. So basically, two new phases arise from the previous one. And okay, so to model this kind of phenomena, you may think that your potential. So let me say that I will focus on the case of phase coexistence. So both in this case and this case, there is a phase coexistence situation given by the fact that there are two phases that I will call -1 and 1, just for simplicity. There are two phases at the same energy, so they are equally advantageous for the system. And so the idea could be that if we call W this double well potential, the material nature is trying to minimize an energy of the form the integral of W of U of X dx. So U is my state parameter whose pure phases correspond to -1. Now, if I do like this, this is not actually a good mathematical problem because basically what happens is that any configuration in which so if U only takes values in -1, 1, then WU of X is 0. So any sharp transition between phases would minimize energy. And this is mathematically inconsistent. So we need to add a singular perturbation to make the problem mathematically consistent, but also physically realistic, because we want somehow the phase change to take place not too often. So we know that, of course, water can become ice, but we don't want this happening without any reason, right? So the singular perturbation is typically something that prevents the oscillation of the candidate U. So the first attempt was to place a gradient type perturbation. So replace the energy function with the integral of, say, gradient U square over 2 plus W U of x dx. Okay, this is a natural choice if you want, and relates. Okay, this relates phase transitions to minimal surfaces. Well, and this is an observation due to Gertin, Modica Mortola, Sternberg, Caffarelli, Cordoba, and so on, depending on the point of view and the result you want. But the basic idea is that you want to, first of all, look at the material from far. So you replace U with some U epsilon that is U of x over epsilon. So as epsilon goes to 0, you have a macroscopic view of the material from far. This would basically change. Well, if you do this, the energy functional would become, I think, epsilon square gradient U square over 2 plus W of U of x dx. But tradition prefers to multiply by 1 over epsilon this quantity. I mean, this is what you would get using this transformation, but this would make the energy blow up when epsilon goes to 0. So it's convenient to multiply by 1 over epsilon. This energy would actually remain bounded. And so as epsilon goes to 0, what you can guess is that minimal surfaces are produced. So without giving a full proof, let me show what the motivation is. So basically, if we call this F epsilon, well, F epsilon, if I do Cauchy-Schwarz, is bounded from below by the integral of the gradient of U epsilon, what is the square root of W U epsilon. This is just Cauchy-Schwarz, and I'm probably forgetting some factors. And then you may think that this is actually by coarea also. So this is Cauchy-Schwarz. This is coarea. This is the integral dt on the level sets of U epsilon. Well, on the level sets of U epsilon here, I can write just W if I want. This is, say, the measure, the n-1 dimensional measure on this set. And then I can think that U epsilon, in order not to make this contribution, the potential contribution diverge, should better converge to either 1 or -1. So we can easily guess that U epsilon converges to a function which takes value 1 or -1. So if I define E to be the set in which the limit of U epsilon takes value 1. This is just a characteristic function. So if I can pass this to the limit, well, this would be just a constant that comes from this integral of the square root of w, which I normalize to be 1 for simplicity. And then this is just hn minus 1 of this interface. Because I imagine that all these sets converge nicely to the final interface. Okay. Every step here has to be justified, of course. That's why we needed cool people to make the theory work. And also you have to somehow guess that the minimizer is trying to attain this inequality as much as possible. Again, this has to be justified, and people invented gamma convergence to make this as a serious mathematical statement. But so the bottom line is that phase transitions are related to minimal surfaces. And ultimately to surface tension. So you may think that the model that the minimal surface is considering is a mean field. I have more space here. Okay. That's nice. So minimal surfaces wow, that's technology. So minimal surfaces are, in a sense, a mean field model, in the sense they come from an averaging process. So the surface tension which is what somehow makes the surface minimal, because the surface tension tries to minimize the area in contact with the atmosphere. Well, the surface tension is actually an average of long-range interaction. So if you suppose that you have some water, well, what happens for a particle here is that there are other particles of the water around, but it's basically a very symmetric situation, because the particle on the top push up, the particle on the bottom push down, same on the left and right and in any direction. So a particle here does not feel the influence of surface tension. On the other hand, if you have a particle here, the situation is very asymmetric, because the other particles will attract it. So from the bottom, it will be attracted. Here will be attracted, here will be attracted, here will be attracted, but there is no compensation from the top. And this is what creates the idea that the surface tension is a very local object that only takes place at the boundary of the set E. So for me here, the water is representing the set E. However, I mean, all these arguments has two complications. So at the level of the phase transition, we are taking a singular perturbation which only accounts for local perturbations. And this influences the fact that in the limit we obtain a very local object like the classical surface tension. But the fact is that if you want to look at the material at a nanoscale, the situation is different, in the sense that if you, now it's just a picture, right? But if you take a particle here in which the distance is basically at the same scale or comparable scale at the size of a molecule, then one has to take into account not just the average of the interaction, but something more accurate. So it would be very desirable to have a model that can describe surface tension and phase transitions as a whole, but this is not possible as far as I'm aware of. So what people try to do is try to separate layers or separate scales, and to look for models which can describe more or less what happens at a given scale. So what I would like to speak about are these models in which one considers long-range interactions with a polynomial tail. So the polynomial tail is technically important because one wants to put something which is decaying at infinity because the force is decay for large distances, but it doesn't decay too much like exponential, which would kill new phenomena. Then, well, other natural assumptions, these are just for simplicity, is that it's the interaction is rotationally and translationally invariant. Well, this can be relaxed, but it's the natural assumption that makes things easier. And also I will focus on the case in which there is an invariance under scaling. This can also be relaxed a little bit, but it's important to prescribe something that allows a blow-up to be justified. So we want to understand what happens near a particular configuration. We want to blow up and to get something which makes sense. Okay, so in this setting, the typical points at interaction is that if one has two sets, A and B in Rn, the interaction between A and B, say, and A and B are disjoint, the interaction between A and B is the integral over A, the integral over B of x minus y to the power n plus 2s. And here let me put a factor which is 2s minus 1. I mean, this factor at this level is not important. It will be important just for consistency if I pass to the limit. But this is basically, I'm translating these conditions into a pointwise interaction. So the idea the idea that was considered by Caffelli, Rojoff, and Savin, and also the previous paper by Visentin from another point of view, is that one can define a notion of fractional perimeter. So here S is a parameter between 0 and 1/2. One can consider a fractional perimeter say fractional perimeter of a set E, which is just the integral between E and E complement of x minus y n plus 2s, which is, if you want, the interaction between E and E complement. And so now the situation is different. I would say it's more explicit than before. So if we have a set E, the non-local analog of surface tension is not localized just on the surface. Of course, on the surface, this denominator will weight a lot. So interactions here will be very dominant, maybe when S is large. But still, every point interacts with everything else. So this point here interacts with this as well, just the interaction is weaker than the one close to the surface. And well, and actually you can also localize this notion considering the S perimeter of the set E in a given domain omega, just considering all the interactions for which omega takes place. So maybe I don't want to write it because it would complicate it, but the picture would be something like this. So I have my reference domain omega, and I have a set E. I put here all the interactions between E and the complement that involve the domain omega. So I take this point again, this point, this point again, this point, this point again, this point. And I don't put the interaction between these 2 points because they both lie outside omega. So this is the contribution of 3 terms that account for this. And I will consider non-local minimal surfaces as the critical points. Well, let's say this. I will consider the non-local minimal surfaces as the local minima of this function. Okay. Okay, so there are several questions. Let's see if I can try to answer some of them. So, well, the first is this useful? The second is this related to phase transitions? The third is does this produce any new stuff? And let's see if we can say something about it. Well, it is useful. Well, of course, the notion of usefulness in mathematics is a bit subjective, but let me show you at least one case in which this technique is obviously useful. And this has to be the very simple problem of computing the perimeter of a square. Now, when the first time I've seen the definition of perimeter according to Cacciopoli or De Giorgi, I have to say I was a bit arrogant and very skeptical. I said, okay, these people are making life too complicated. I know what a perimeter is because I've been taught the perimeter in elementary school. Why do they need all this complication? And then I will show you an example that actually says that Cacciopoli and De Giorgi were right. I mean, perimeters are hard to compute, even in obvious cases, because then, I mean, the justification that you find in books are crazy counterexamples that you feel, okay, too hard. There must be something easier to appreciate that perimeters are difficult. And the easiest thing that you can do is to ask your computer to compute the length, the perimeter of a square. So you take a square, you have your computer, and your computer has pixels on the screen. And your computer is very expensive, so the resolution of your computer is very high. The side of a pixel is epsilon, and epsilon is very small. And then you give your computer a square. The square is side 1. And so from elementary school, you know the perimeter is 4. But the fact is that your computer will digitalize this image, for instance, by replacing, using the pixels, right? It will replace this side by the analog, but with the pixels. Now, if you do that, any infinitesimal length is actually multiplied by square root of 2 due to Pythagoras theorem. So the error in the perimeter, for the classical perimeter, in this case, is equal to 4, I think, square root of 2 minus 1. And this is bad because no matter how expensive your computer was, epsilon can be as small as you want, the error is not going to 0. And this is very unpleasant for practical purposes. On the other hand, the error for the S perimeter, well, the error for the S perimeter is better because in every little pixel, well, the error comes from these blue pixels. In every blue pixel, the error comes from the scaling of the perimeter, which is, well, I erased it, but if you think, the scaling is like epsilon to the n, which in this case is 2, minus 2s, so it is 2 in this case. This is just the scaling of the interaction. And then this is coming from each pixel, but the pixels involved are like 1 over epsilon. But then this is not too bad because this is now epsilon to the power 1 minus 2s. And since epsilon was less than 1/2, this is a good error that goes to 0 when epsilon goes to 0. So there is at least one simple case that tells us that the classical perimeter is somehow unstable, while this new version of perimeter is, in a sense, more consistent and flexible. Okay, so this, I think, ticks this box. Well, is this related to phase transitions? Well, it is because in principle, I could do the same here. So at the level of phase transitions, I could add here a singular perturbation that accounts for all point set interactions for instance, of this form. Well, I could still scale it like this and obtain, well, maybe not this, but I do the same procedure. Now, I don't write the details, Because if I write the details now, it will be overly complicated because I have to scale. But then you remember before I was multiplying by 1 over epsilon, and that was working. Here you have to multiply by the right quantity depending on epsilon and s. But once you do that, you get a function that I call f epsilon of u epsilon. Well, the relation between phase transitions and non-local minimal surfaces is that as epsilon goes to 0, f epsilon of u epsilon converges, well, in the gamma convergence sense or in the level set sense, to what? Well, there is a little thing here to be considered, is that this is well defined for all s between 0 and 1, while the non-local minimal surfaces are well defined only for s below 1/2. So this suggests that something strange happens here. And what happens is that as epsilon goes to 0, the convergence of this functional is to the classical perimeter, say as, let me say, the perimeter of E, where E is the limit of the U epsilon, as, so this, if S is above 1/2, and the S perimeter of E, if S is below 1/2. So this is interesting because it's telling us that non-local singular perturbations of phase transitions have two different types of behaviors. Of course, the functional for a given epsilon is non-local, but when S is above the threshold 1/2, the big picture localizes. So if I see my material at a large scale, what I see is actually a local behavior. But when S is below 1/2, the non-local structure of the phase transition is genuine, is persistent at a large scale. Oh, and this was done together with Ovidiu-Savin. So this is also thick. How much time do I have? Okay, so let me try to convince you now that this produces some new stuff. So it would be desirable to appreciate the non-local effect on these new structures. So one first thing that I think is new and interesting is this phenomenon that we call the stickiness. This is done with Serena Di Pierro. Ovidiu-Savin. And I don't think we ever gave, yes. Yes. Okay. No. So I don't think we ever gave a precise definition of stickiness, I think that it's more suggestive to look at the phenomenon, and the informal definition is that non-local minimal surfaces have the strong tendency to stick at the boundary, differently from what happens to, for instance, classical minimal surfaces. So for classical minimal surfaces, you have basically no reason to stick at the boundary. Well, you can produce examples of stickiness. So let me give a silly example. So suppose that you have a ball and you take as datum in 2D, right? You take as datum for your surface, which in this case is a curve. This one, well, the solution is, of course, that you join these 2 points with a straight line. So you cross the boundary transversally. Now you can produce stickiness a posteriori, because now you can erase this part of the domain, move it, and get something like this. Now you produce stickiness. But I would say it's unfair, right? You could even produce more stickiness if you keep pushing. So if you keep pushing the domain, then you will have like a free boundary problem in which you have a portion in common with this bean-shaped domain, and then you do something like this, okay? So you can produce stickiness also in the classical cases, but you really have to push against your surface with the very non-convex given domain of reference. But for convex domains, you cross transversally the boundary. Now for the non-local case, the situation is completely different. And so we made a number of very explicit examples. I think the most striking one is this. So you consider, say, a slab like this. So the reference domain omega is this slab here, and as given datum, you have the lower half plane. Now you have to minimize the S perimeter with this datum. Then what is proved in Caffarelli, Rojoffre, and Savin's paper is that in this case, the minimizer is, as you would expect, the lower half plane. This is not already completely trivial. They have to go through a maximum principle to prove this, and to get the maximum principle, they have to rigorously establish the Euler-Lagrange equation in the viscosity sense. So it's a bit delicate, but this is, I would say, really close to the intuition we had. But now suppose that you modify the external datum by adding, let me use again the red, but I think you can see it. You add a small bump, for instance, on both sides for simplicity. That was the original example. You don't really need 2 bumps like this. Now we know how to do it, even if you put 1 bump up, 1 bump down. So the phenomenon is really persistent. But the easiest thing is to think that you put 2 bumps. And these 2 bumps can be placed as far as you want. And they can be as small as you want. Now, in the classical case, putting this type of bumps doesn't change the fact that the shortest length is attained by the segment. But in the non-local case, these bumps are felt. And basically what happens is that the center of the surface is pushed up because it feels these bumps. You can prove that here you are strictly positive, which is fine. You may think, okay, it's new, but still close to intuition. What for me was not so intuitive, I would say, is that the boundary behavior is irregular in a sense. So what happens is that you arrive here without reaching the zero level, and you have a vertical tangency of this type. So if you see what happens here, the minimizer is discontinuous. This was probably the hardest paper for us to publish. It was rejected basically by all journals. At the beginning, the argument to reject it was, this has to be wrong because it doesn't happen in the classical case. Then we had to argue, okay, well, it doesn't happen in the classical case because the quantitative version of this depends on S. And basically, this is, so if delta is the height of the bump, this is delta to a power that I don't remember, but that power is such that in the limit, this height goes to zero. So you don't violate the classical case in the limit. This under the assumption that violating the classical case in the limit would produce a contradiction, which is not even so obvious to me, right? So I'm not sure that the argument to prove that our statement was wrong was fair anyway. But then, but then the argument was that then it must have been known by everybody if that was the case. Okay, so but the interesting thing is that this picture produced some kind of interest by people in numerics. So there is a team by Riccardo Nocetto who investigated these pictures, because so our paper is actually made by a lot of pictures, because to prove this you have to construct barriers, and all the pictures in that paper are done by hand, so they don't mean anything. They're just to visualize the integral computations. And there was a picture more or less like this. And then Nocetto, Lee, and Botagaray use numerics to validate the pictures. And well, the good thing is that the pictures were pretty much fine, except that I may have the psychological tendency to emphasize the steepness. So if this is delta, and this is a power of delta, the picture is not quantitatively correct, right? The power of delta should be much less than that. This looks like delta halves, which is too large, right? But so forget about believing too much in the quantitative scale of the picture. The effect of stickiness visually is very little. And actually, I remember that Riccardo Nocetto told me that it could have been very hard to detect it numerically, because you may think that this is not just a discontinuity, it's just a numerical artifact of the interpolation with the boundary. So they had to carefully look at the numerics to appreciate the stickiness phenomenon. And interestingly, in doing that, they checked the number of other configurations. And for instance, they consider what happened in 2 dimensions depending on the opening of a possible corner. So suppose that so they made 2 numerical simulations. So pretty much if you consider a domain of this form, and the other if you consider a domain of this form. And actually, interestingly, they conjectured that in this case, you have stickiness. So if you place a bump somewhere here, then what happens is that now I don't know how to draw it, right? But something like this happens. Well, again, more or less, I don't believe too much, but so you will have boundary stickiness at this corner. But if instead you have a situation of this type, and you put your bump outside, the resulting picture will have no stickiness at this point. So maybe in the other point, actually in the other points will have, but not at this point. Okay, so there are several beautiful pictures by Nocettoli and Botagaray, and now with Ovidio and Serena, we actually proved that this is true. So the pictures and the numerical conjectures can be proved mathematically. So I think this is a cool thing, because not only it's a new phenomenon, but it's a typical situation in which I don't know, people speak about pure and applied mathematics. Well, in this case, they go together, right? And I find it amusing that typically people may have the impression that nowadays computers do everything. So people run things on computers, and then there are these people called mathematicians who are old-fashioned and boring, and they want to prove what the computers already knew, it, right? I think that in this case, it's kind of nice, because it occurred like, not really the other way around, but still an interaction in which the mathematical theory was developed before the numerical validation, but the numerical validation stimulated new mathematical theory and so on. So I think it's a lucky combination of events. How much time do I have? 8 minutes. I can say another thing which I think it's cool. So this is, well, let me tick the box anyway, because at least we are done. But there is another thing which was done with Eleonora Scinti and Joachim Serra. Well, actually, in that paper, we consider the much more general kernel interaction, but let me just focus on the simplest possible case. And there is a result which I think is very nice, because it deals not only with minimizers. It would be nice, I think, even for minimizer, but it deals more generally with stable critical points of the S perimeter. So in general, one could say, why restricting your attention only to minimizers? Why not looking at all the critical points of the S perimeter? Well, and my first answer to that is that that may be too hard, because there might be too many critical points. So a compromise between specialization and generality is to look at the critical points, which happen to have non-negative second derivative of the energy function. And I will call them stable. And the result that we have with Eleonora and Joachim is this. So suppose that E is a stable critical point of the S perimeter, say in P2. Then the S perimeter of E in V1 is less than a universal constant that depends on n. It doesn't. Sorry, well, both, but you're right. The perimeter. Let me write the stronger one, which is the perimeter. It's true also for the S perimeter, but I think for the perimeter it is more interesting. Well, I think this is a cool result because it's valid for stable critical points, but as far as I can tell, is non-trivial also for minimizers. Because minimizers will have maybe a finite S perimeter, but the perimeter is in a sense already at a higher level of regularity of the S perimeter. So it's already an improving of regularity. It's a little bit because it only goes from S perimeter to perimeter, but it has the advantage of being general because there is no restriction on dimensions, and in being universal. This is different from what happens for classical stable critical points of the perimeter, because for stable critical points of perimeters, you can never exclude the fact that you are dealing, even in dimension 1, with parallel lines. So parallel lines are a stable critical point of the perimeter, but you can produce, in the classical case, well, suppose that this is B2, this is B1. You can never rule out the possibility of having an infinite or an arbitrarily large, say, number of parallel lines. So in this case, you would have a perimeter in B1, which can be as large as you want. So the non-local case, it's better. Well, it's better exactly for the reason for which it's worse. So there are points that interact to each other. So somehow these layers tend to repel. They are not very comfortable to be pushed one against the other. So what happens in the non-local case is that there is a sort of merging of ends. So, and this is just a picture, right? The theorem is this, but if you have to interpret it, you can try to violate it. You can say, no, I put lots of ends, and I hope that these ends survive in B1. So I force, for instance, I force a configuration like this at infinity, okay? Well, what happens in this case is that ends will merge probably before reaching B1, so something like this. Or will die, for instance, this can die, this can die, these two can merge, this can die, like this, right? Well, some will probably go through, right? So maybe these will go through. Something may well survive. I'm not excluding this, of course. But if you prescribe too many ends, they will have either to merge or to die before B1. And I think this is another nice new phenomenon. check this again. And maybe my time is over, so I better stop here.
I have a comment and a question. So a comment is about point 2, actually. And the question is about the last result. So about point 2, well, I will have a different explanation actually for the connection with phase transitions, which is mostly related to easing models. Okay. So in that case, it's just so that kind of interaction is a sort of a dipolar interaction between the spins. And then you expect to see something like that, but not so well. There is a question related to it. I don't know whether it is proven. I don't think so, right?
Okay, that's an interesting question because there is a paper we have with Serena and Matteo Cozzi, which does exactly like this. So if you take a spin model like easing, and you put a power-like interaction between spins, and you scale properly, the spin model is discrete, right? But if you scale the distance between spins,
you take the discrete to continuum.
Discrete to continuum, then you get non-local minimum.
Oh, that's very good. So that's very interesting. And the other question is about this last problem. So how much does the result depend on the fact that you consider a ball?
Oh, no, it doesn't depend. I mean, B1 and B2 are just names, right?
So it could be a square, and then you get the same.
Could be a square. I mean, the only thing that I need is that the domain inside is separated from the domain outside.
Okay. Okay, thanks.
Other questions? Comments?
I have just a curiosity. In the local case, it is known that there is a connection also between the parabolic Allen-Cahn equation and the mean curvature flow. Have you developed the theory also in that direction?
That's a good question. I'm not 100% sure. I think that there is something by even some Yo maybe about the parabolic case, but I don't have a reference on the top of my head.
Thank you.
More questions? Filippo?
This is kind of professional deformation. Okay, so when you speak about non-local problems, you have something which is quite, let's say, my own point of view of non-local problems, it's a little bit different because I have this obsession of suspension bridges. When you showed that picture, I mean, you plotted this picture using red chalk of these bumps, this immediately came to my mind that I have a very nice video, which I can give you, on the non-local behavior of bridges, which basically says exactly what you mentioned here. You do not see discontinuity because, that makes the bridge collapse. But, I mean, if you have a beam, non-locally, you have a deformation which is due to the cables, and you really see the effect. So if you want, I can give you the video.
Yes, no, I'm very interested. Yes, so let me, maybe I have to say two things. One is that I say non-local, but I'm cheating, right? Because this is a very special non-locality, right? Non-local is much bigger than this, I agree. The other thing is that maybe I should have mentioned a connection with crystal dislocation, because here I'm trying to convince you that non-local stuff is interesting by modifying the local counterpart. But there are a number of instances in which the problem you start with is classical and local. But as you said, the problem in itself introduces a non-locality. And so, for instance, when you study the Piles-Nabarro model for crystal dislocation, Piles and Nabarro wrote it as a PDE in R2. But it may be convenient, and for instance, this is a line of research we developed, to think that it's not a PDE in R2, but it's a non-local PDE in R. The reason to trade non-locality for dimension is that at least in dimension 1, you have a number of techniques that come from dynamical systems. And so it's true that the situation is more complicated technically, but you have more weapons to use. So I agree that there are types of non-localities coming from the classical world that are already encoded there.
Okay, no more questions? Not, we thank again the speaker.
Thank you.